Hey guys, Lainey here, and today I will be walking you through my understanding of the structural design process using a Chick-fil-A building as an example. This includes how we establish design criteria, determine loads, develop the vertical and lateral load paths, and ultimately design the framing and foundations. Every structural design begins with identifying the governing codes. It is important to determine where your project is located, as specific variations of the IBC and ASCE 7 vary by city and state, since different jurisdictions adopt codes on different cycles. Once the applicable codes are established, we determine the building's risk category, which is based on use and occupancy. Restaurants such as Chick-fil-A are usually risk category 2, whereas essential facilities such as hospitals are typically risk category 4. The risk category influences importance factors in wind, snow, and seismic design. Once all of these are determined, you can use the ASCE 7 hazards tool in combination with the specific ASCE 7 version, risk category, and site soil classification determined from the geotech report to determine the basic wind, seismic, and snow loads. This step sets the foundation for all subsequent calculations and design decisions. The next step is defining gravity loads. These loads are project specific, so it's important to collaborate with architectural, mechanical, electrical, and plumbing engineers to determine what loads are going to be on your structure. Dead load includes the self weight of the structure along with any permanent architectural and MEP components. Live load accounts for occupants, furniture, and movable items, and may be reduced depending on the number of floors and tributary area. Roof live load is typically 20 psf, but can always be reduced up to 12 psf for larger areas. Snow loads can significantly influence roof design, especially when parapets or elevation changes create drift conditions that concentrate snow in specific areas. Flat roof snow load is determined by taking the ground snow load and multiplying it by zero point 0.7 times the exposure factor, thermal factor, and snow importance factor. The flat roof snow load is your base design load that snowdrift can be added onto. In regions where the ground snow load is less than 20 psf, it's important to consider rain on snow surcharge, which is an extra 5 psf that will be added to the balanced snow load, but does not need to be combined with snowdrift. For snowdrift, the drift height is calculated by summing the balanced snow height, HB, and the drift surcharge height, HD, where HB is the flat roof snow load divided by the snow density, and HD is obtained directly from the ASCE 7 drift graph. The drift width, W, depends on whether the total drift height exceeds the allowable drift height. If it does, the drift footprint widens accordingly. These concentrated drift loads often govern joist and deck design because they create large, localized forces that differ significantly from uniform snow loading. In order to establish the main wind force resisting system, we use ACE 7 directional procedure and apply all required wind load parameters to calculate the velocity pressure. The process begins by determining the building's risk category and selecting the appropriate basic wind speed from the ASCE wind maps. From there, we identify key modifiers such as the wind directionality factor, exposure category, topographic speedup, ground elevation factor, and the gust effect factor, all of which influence the magnitude of the applied wind forces. We then determine the enclosure classification, which drives the internal pressure coefficient and can significantly affect net pressures on walls and roof surfaces. After establishing these parameters, we calculate the velocity pressure using the appropriate exposure coefficient and then apply the external pressure coefficients for the specific roof and wall geometries. Parapets play an important role in wind design because they are considered part of the main wind force resisting system and must be designed for the global wind pressures acting on the building envelope. Even though they are relatively small elements, parapets experience amplified pressures due to flow separation at the roof edge, and these forces must be transferred into the roof diaphragm and supporting framing. After addressing parapet forces within the main wind force resisting system, we move on to components and cladding, which is governed by localized pressures based on tributary areas. Elements such as roof panels, wall panels, fasteners, and trim pieces fall under components and cladding design, and they often experience higher localized pressures than the global main wind force resisting system loads. ASCE 7 requires engineers to use components and cladding pressures when the tributary area is below a specific square footage threshold, ensuring that small elements are not under-designed. The CP coefficients and L over B ratios help determine these localized pressures. The soil site class can have a positive impact on how seismic forces are transmitted through the ground before reaching the structure. Oftentimes, geotechnical reports can provide soil site classes that are better than the default site class of D, which in turn allows you to reduce overall seismic demand of the structure. We determine the seismic design category, which reflects both the building's importance and the expected level of seismic hazard at the site. From there, we follow the equivalent lateral force procedure to calculate the base shear using the spectral accelerations, the importance factor associated with the risk category, and the effective seismic weight of the structure. We then determine the building's fundamental period, which influences how much of the seismic demand is applied, and apply the appropriate response modification coefficient R. The R value represents how much inelastic behavior the lateral system is expected to undergo. A higher R value corresponds to a more ductile system, meaning that the system is intended to accommodate larger inelastic demands, and as a result, is designed for lower seismic forces. Because seismic design assumes this controlled inelastic response, we use capacity based design for collectors, braces, and anchorage so these elements remain stronger than the intended ductile components. Finally, the seismic forces are distributed vertically through the structure based on mass and height, ensuring that each level is designed to resist its appropriate share of the total lateral load. Once loads are established, we have to define the load path that goes from the roof down to the foundations. For vertical loads, the roof deck transfers load to the joists transfer load to the beams transfer load to the columns, and the columns transfer loads to the foundations. For lateral loads, the roof acts as a diaphragm to resist wind loads from the walls. The steel framing requires bracing to collect the lateral forces due to wind and seismic, which in turn transfers the load to the footings. The roof framing system begins with the roof deck, which must be checked for the allowable load capacity, which is based on the maximum span between the supports, or in this case, joists. Loads from the deck are transferred into the joists, which are typically delegated design elements. The engineer of record provides the joist manufacturer with the required live load, total load, uplift, any snowdrift conditions, and the appropriate joist type, whether it's K, KCS, TCX, LH, or DLH. The joist depth required varies with span, and tools like Volcraft's Economic Joist Design Guide make it easy to identify cost effective options. These joists then frame into the beams, which must be designed for the governing load case. Depending on how many joists frame into a beam, the worst case scenario may be controlled by multiple point loads on the beam or by an equivalent uniform load. Buckling is likely to control the design due to the columns being unbraced over their full height, so it's important to check for slenderness when determining your column sizes. The connections between framing elements ensure continuity of the load path and must be designed for the appropriate shear and moment demands. For diaphragm design, the roof is treated as a simply supported beam, where both of the reactions are technically considered the two lateral frames. This allows us to determine the shear forces that cords and collectors must resist. The roof diaphragm fastener plan reflects this behavior. Shear is highest at the perimeter and decreases towards the center, so fastening patterns can often be reduced as you move inward, providing the roof is large enough that multiple patterns are economical. Braced frames are designed to collect lateral loads and transfer them to the foundations. These braced frames are usually designed similarly to columns due to the fact that the compression typically controls bracing size because of buckling. It is important to note that the design of the connection at braced frames should be designed for tension to allow failure of the brace prior to the connection in the case of a seismic event. Finally, the foundation system, which in this project is isolated footings, is generally sized by taking the column load and dividing by the allowable soil bearing pressure and taking the square root of that. On smaller footings or braced frames, uplift from wind can govern the design, requiring careful checks of anchorage, overturning, and soil resistance. These components collectively complete the vertical and lateral load pass from the roof all the way to the ground. The design process of a Chick-fil-A brings together every major aspect of structural engineering, from establishing code criteria and defining environmental and gravity loads to developing the vertical and lateral load paths and designing the framing and foundation systems. By working through wind, snow, seismic, and load path considerations step by step, we ensure that each component of the structure performs reliably under both everyday conditions and extreme events. This process reflects the balance between code requirements, engineering judgment, and constructability that defines real world structural design. Understanding how these pieces fit together provides a strong foundation for approaching projects with more confidence and clarity. Thanks for watching.